Welcome to part 4 of the example problem for solving indeterminate structures using integration. This portion determines the deflections as a function of x by integrating the rotation equations, and introduces the boundary conditions for point A, point B, and point C. The deflections, all these points have to be 0. We've established these as our equations for the rotation of the beam from A to B and from B to C, respectively. And so when we want to know the deflections, which will be really where we can get a lot of things figured out, because that's where these boundary conditions are, right? These boundary conditions of B and A and C, these are boundary conditions for deflection, holding them to 0, not rotation. So these are free. It's free to rotate however it dang well pleases, but it better have a deflection of 0 at A, 0 at B, and 0 at C. So we're just going to need to integrate one more time, right? Because from A to B, the deflection is going to be the integral of the rotation from A to B. And similarly, from B to C, the deflection is the integral of the rotation from B to C. So this first one will go down real easy, and actually this one will also be just as easy. The only thing is that these constants, right? A is not a function of x, B is not a function of x. The constants for integration are certainly not a function of x. So these are just long terms for very simple polynomial. So let's do AB first. That's just going to end up being, I'm not going to write everything out a million times, right? It's the integral of this term right here. Open up brackets for the Young's modulus and second mole inertia. You see I ran out of space here, had to tack it on right there for that one. So we've got, that's going to be negative x to the 4th kips over, that's going to be 24 feet now, plus AY, that's x1 cubed over 6 plus some constant integration C3 over EI, and I'm just going to put the constant integration out here because excuse me, that should be fifth constant integration. But right away, right, because like I said, we don't have to deal so much, or we can do some good work with these boundary conditions we've got at A and at B and at C, and those boundary conditions are going to tell us, well, what's the deflection got to be at A? It's got to be 0. So if we plug 0 in for this, oh, excuse me, I got all excited finishing this. There should be an x right there. Duh. So what we're going to end up with is, if we plug 0 in for this, that turns 0, that turns 0, that turns 0. That has to be 0 as well. So we don't have to worry about that constant integration. Now this is going to be, well, it's going to be a long function. But let's just do it. The deflection from B to C is a function of x 2 is equal to 1 over the Young's modulus and the second moment of inertia times negative x2 to the fourth divided by 24 feet. Also its kips. Try to maintain all your units throughout this. It'll save you a heartache in the end. Plus this term AY plus BY minus 6 kept divided by 2 x2 squared. Sorry, that's cubed, and this is to the 6. What am I doing? I'm just copying these things down. Plus 6 feet AY minus 18 kip feet x2 squared. Divide that by 2. And then add in 18 feet squared AY minus 36 kip feet plus that constant integration we haven't figured out yet, C3, but at least we don't have to deal with C4, times some x2 plus some constant integration C6. Now, once again, fortunately, we've got this boundary condition going on right here. And that boundary condition tells us that C6 also has to be 0. And it's got to be 0 because there sure as heck ain't any deflection going on right there. Okay, so now we've taken care of, we considered the boundary condition for AB for this point, and we've considered the boundary condition for BC for this point. We need to consider the boundary condition for AB for B, and the boundary condition for BC for C on BC. Let's start with AB. That's much easier to deal with. We know that if we put in 6 feet to AB, we better get 0, right? Because, well, there's a roller right there. So, six feet into that, we're going to end up with, well, we know it'll be 0. I'm going to move that over there because we don't need it. Multiply both sides by the Young's modulus and the second moment of inertia. So, negative 6. So let's put that in parentheses. 6 feet to the fourth divided by 24 feet and multiplied by kips. Let's not forget that. Plus AY, still don't know what that is, times 6 feet. Cube that one. And then divided by 6 feet. Cool. Plus some constant integration C3 times 6 feet. And that's got to equal, got to equal 0. And that's gonna, let's just rearrange this, you know, and divide that by 6 a couple times. Yeah. 9 kip feet cubed minus 6 feet cubed times reaction AY, which I realize is not a proper number. It's still a function of AY, but now that we've done this, we've reduced the number of variables we're working with. We can use this instead of C3. Like, for example, up here. Now this is going to be very long, right? But it's just one equation. It's just one polynomial. As it is, let's just go for it, right? Has to be 0, and it's going to be, and again, I'm just going to move the Young's modulus and the second moment inertia over here, because 0 is 0 is 0. Negative 6 feet to the 4th over 24 feet plus AY plus BY minus 6 kips divided by 6 times 6 feet cubed plus 6 feet times AY minus 18 kip feet divided by 2 times 36 plus you know what? Let's submit defeat and start a new line. Plus 18 feet squared times AY minus 36 kip feet plus this 9 kip feet cubed minus 6 feet cubed times AY times x2 has to equal 0.